The internet is often treated as a magic box. You click a link, and data simply appears. But beneath that seamless user experience is a physical reality governed by engineering architecture. Data communication relies on a rigorous stack of discrete technologies. It is a layered system of physical transformations and logical routing protocols working in tandem. The core engineering challenge at the base of this stack is moving discrete digital bits, ones and zeros, across vast, noisy physical distances without losing their integrity. To solve this, we have to start at the most basic physical layer of reality. Before a single bit of data can be routed across the globe, it first has to be translated into electromagnetic energy. Once that physical transmission is stable, the system has to scale. It requires routing logic to connect billions of independent nodes together without the entire network collapsing under its own weight. Every network architect must balance these two competing forces, ensuring reliable, error-free physical transmission on the wire while designing efficient data routing paths through the broader system. To understand how internet infrastructure functions, we need to build the model from the bottom up, and that begins with the physics of a simple wave. The vehicle for all data transmission is the electromagnetic wave. By running an electric current through a wire, we generate a field, projecting energy outward into open space or along a physical track. This diagram illustrates the concept of a carrier wave. It maintains a uniform shape, acting as a blank canvas. On its own, a perfect carrier wave transmits no information. To send data, it must be intentionally altered through a process known as modulation. In amplitude modulation, or AM, the digital ones and zeros are represented by changing the height of the carrier wave. The peaks grow larger or smaller to match the discrete digital input. Alternatively, frequency modulation, or FM, represents that same data by altering the speed of the wave's oscillation. The wave compresses and expands horizontally, while its height remains perfectly uniform. When we move away from open space and send these signals down physical wires, we have to determine how the channel is utilized. The most direct method is baseband signaling. As noted in the lower left section here, baseband utilizes discrete digital signals. These pulses occupy the entire capacity of the wire. Right below that is broadband signaling, which instead uses continuous unidirectional analog signals. Because broadband signals are assigned different frequency channels, multiple separate data streams can be multiplexed, meaning they share the exact same physical medium simultaneously without colliding. Whether an engineer uses baseband pulses on a copper lyre or broadband waveforms over the air, modulation is the necessary bridge. It translates strict computer logic into physical phenomena capable of moving through the real world. Once data is modulated into a signal, it requires a designated physical pathway to guide it to its destination. Looking at the top left of this chart, we see the primary wired transmission mediums: twisted pair, coaxial cable, and fiber optic. These guide either electrical currents or light pulses. Fiber optics provide significantly higher data throughput than copper alternatives. By using total internal reflection, these tiny glass channels bounce light over vast distances. For environments where wires are impractical, data relies on wireless mediums. Here, broadband analog waves are beamed across open space using highly directional microwave dishes. Network architects organize these various interconnected mediums into rigid hierarchies based purely on their geographic footprint. At the smallest scale, personal area networks, or PANs, handle short-range connections like Bluetooth. Scaling up, local area networks, or LANs, connect a single building via Ethernet. Finally, wide area networks, or WANs, form the massive infrastructure connecting isolated LANs. This geographical scaling introduces a compatibility problem. The localized digital logic of a LAN cannot communicate directly with the analog long-haul infrastructure of a WAN. That boundary required a vital translation device, the modem, short for modulator-demodulator, positioned exactly at the border of these two networking scopes. The modem bridges the gap by taking a local computer's raw digital baseband data and translating it, modulating it, into analog broadband tones that the WAN can carry. As network scopes scale from a single desk to a global population, reserving a dedicated wire for every active connection creates a massive infrastructure bottleneck. To support more users, the network needs a more efficient way to share the line. Early global networks faced a severe scaling bottleneck. They were highly inefficient at utilizing the available physical transmission mediums. The evolution of commercial cellular networks provides a clear historical case study for how engineers addressed this exact bottleneck. This hand-drawn telecom matrix tracks the architectural jump from early 2G voice networks to 4G data networks. Looking at the 2G column and the GSM standard, we see the architecture known as circuit switching. The limitation of circuit switching is that it monopolizes a continuous physical line between 2 points for the entire duration of a session. If no data is actively flowing, that capacity is wasted. The solution was the transition to packet switching, which debuted under the GPRS standard. Packet switching abandons the dedicated line. Instead, it dissects large data files into tiny, uniform chunks called packets. Each packet navigates independently through a shared web of routers before reassembling at the destination. Because no single transmission needs to hold a line open, thousands of users can transmit data over the exact same physical infrastructure simultaneously. This structural change created efficient, always-on network states. By divorcing logical connections from dedicated physical wires, packet switching bypassed the capacity bottleneck, providing the structural foundation for the global internet we use today. Even with the efficiency of packet switching and the clarity of fiber optic mediums, data communication is ultimately constrained by rigid mathematical limits. Every network's performance is dictated by the tension between two specific parameters, bandwidth and latency. On the left margin, bandwidth is defined strictly as the overall capacity of the communication channel. Think of bandwidth as the sheer width of a pipe. It dictates the maximum volume of bits that can be pushed through the cross-section of a network simultaneously per second. Below that, we see latency. Latency contrasts entirely with bandwidth. It governs the absolute speed of a single signal traveling across physical space. Measured in milliseconds as round-trip time, latency is limited by the speed of light, geographic distance, and the processing delay incurred at every router hop along the way. This creates a performance paradox. A connection can have a massive bandwidth capacity, but if the distance between servers creates high latency, the resulting user experience will still drag. Modern data communication is an ongoing engineering war against physics. It requires shaping analog waves to maximize bandwidth, designing packet switch topologies to manage scale, and fighting the speed of light itself to minimize latency across a global wide area network.